Hello everyone. I hope you all are doing well. And this is first in the series of webinars on embedded systems and Internet of Things. Now, before getting into the world of Internet of Things, I just want you to know that the buzzword IoT in the recent years has made the term very ambiguous, and we all know that Internet of Things comprises of systems, some particular system connecting to the internet, but that's just not really it, because IoT has always been a part of our uh, ecosystem, technological ecosystem, but we it just become a very big word in the recent years, and so it's very important that we know what are embedded systems, because it's an integral part of an IoT ecosystem. And before getting into the world of IoT, uh, one should know what are the basics of embedded systems, what are the components that really consist of this IoT ecosystem. And so embedded system, any system with some peripherals, with some inputs and outputs, uh, uh, this kind of system, it plays a very important part in an IoT ecosystem. So if you want to design and develop an IoT ecosystem or any other modules related to it, then I think it's imperative that you should know about embedded systems first. So before going forward, let me tell you something about myself. My name is Gaurav Sharma, and for the last 3 years, I've been working in the field of embedded software development, and majorly in the domains of smart metering, IoT integration, and digital audio signal processing. Uh, During these 3 years, currently I'm working with Cisco as a software engineer with the uh, Nexus switches and routers business unit. So my responsibilities are pretty much designing and developing the software modules on top of these products, and provide support for them. So that's pretty much about me, and let's get ahead with this video. Let's do the basics. But yeah, why do we need to brush up the basics? Now, what I've realized over these years is that 3 years of my professional career, that you know at any point in time, you would want you would need to get on with the basics of any subject. Now, why is it really important to brush up the basics of any other subject, not just the embedded system? Let's just take this subject aside, embedded system, and let's just take any other subject. Why do you need to brush up the basics of that subject? Well, partly because that you need to build a very good foundation on top of it, and if you don't do that, then chances are that you would not be able to understand the complexity of a system. Now, in order to understand the complexities and the depth of a subject, it's very important to know the basics around that subject, so that you can build a very good, very robust foundation on that subject. So we'll get on with the basics first. We'll get to know what is an embedded system, the parts of embedded system, components of an embedded system, and before designing and actually developing a software on these embedded systems, I think it's very important to know what are the basics of embedded systems, and some intricacies, some details of these embedded systems, and any other information related to this subject. So let's get on with the part. So what is an embedded system? It's basically a combination of a hardware and software relay. You know, it is an amalgamation of a software that is put inside a hardware, so that the hardware is able to perform a task, so that that hardware is able to accomplish some task. So whenever we talk about a system, whenever we talk about an embedded system, we talk about memory as well. Now, a memory is just a storage. It's not really a storage, but in the vague sense, it's not really justified to say that storage is memory. But whenever we talk about memory, there is one thing that comes to our mind, which is storage, storing. storing some data, storing some software. So in embedded systems we have mainly two kinds of memories. We have ROM and RAM. Now here we won't talk about much in the detail of ROM and RAM, just that you should know that read only memory is that kind of memory whose content cannot be changed during a runtime. So whenever you are running an embedded system, whenever it is already powered up, you won't be able to change the content of a read-only memory. Whereas in a RAM, you would be able to change the content of that memory in the embedded system. So whenever you want to put a software in a hardware, and you want your software to run continuously in an embedded systems even after you power it back on, so you're supposed to put that particular software in a read-only memory, because read-only memory is that part of memory which is non-volatile, which is not which does not vanish after you power it off. So if you power off your system and if you power it back on, what is that one particular part that remains in the system even when it is powered back on? So for example, if you have a software, if you have put a software in your system, in your small embedded system that just blinks the LED, and you have put some instructions into your controller, and if you switch off the device and then you switch back on, then those are the instructions that are stored in the read-only memory that are retained, and that will be executed from the start, and those content will not be deleted even if you power off the device. But RAM is that part of memory which is volatile, and which is very much volatile, and you will lose the content of that memory if you power off the device. So basically RAM is used in the scenario where you have to perform some intermediate operations, you have to perform some processing to your data, and this data is just intermediate, and you just need this data, you just need this content whenever you are powering on the device, whenever the embedded system is powered on, then you use this random access memory. So that's RAM for you, random access memory. Now moving on to the parts of embedded system, mainly an embedded system has a processor and input output devices. So a processor is anything that processes and computes using some operation. Now for example, if you have some inputs of sensors, and you want to fuse the data of those sensors, and you want to compute you want to compute some operations, some arithmetic operations, some logical operations on top of that data. So for example, if you have a temperature sensor, you want to add that data to your humidity sensors. So what you will do is the controller, the embedded system, will tell the processor that I want to add these values, I want to multiply these values, I want to divide these values, and give me the resultant, give me the result of this operation. That's where the processor comes in. That's where the processor is used to process, to compute these operations effectively using their arithmetic logical unit. In the later point of this video, we'll get to know what are the components of a microprocessor and microcontroller, but right now, for the time being, it's sufficient to know that a processor is any device or any component which is able to process and compute using some arithmetic and logical operations. These operations may be anything. These operations may be dealing with the data of sensors. These may be dealing with your manual data. So this is processor. That's where the processors are used. The other component of an embedded system is input-output device. Now, as the name itself suggests, input means that you are taking the input from somewhere, and it may be from anywhere. For example, it may be from your surrounding. A sensor is usually known to sense the quantity, sense the parameter of its surrounding. That parameter may be anything. Maybe let's take an example of a temperature sensor. A temperature sensor senses a temperature around that entity. A humidity sensor senses the humidity. Now these sensor, what they basically do is they convert this parameter, they convert the temperature. The temperature sensor convert this temperature, the physical temperature, the physical parameter of the surrounding, into a digital parameter. Now the one thing that you need to focus here is the sensor is sensing something that a normal human being is not able to quantify. So for example, if you are watching this video from your home, and there is one particular temperature which is maintained in your room, maybe the room temperature, then you would not be able to tell that what exact temperature is being maintained in your room unless until you quantified it, unless until you digitize it with some block, with some system. So that's where the sensors come into picture. So they basically quantify this data. It tells you what is the exact value of this physical parameter, so that a computer such as an embedded system, such as in the embedded system, would be able to act on these values and produce an output. Now speaking of output is anything that produces a result. Now the most simple example of an output is an LED. These LEDs are usually used in the scenarios where you have to give some status in a system. For example, if I talk about routers and switches, there are basically 6 or 7 LEDs which tell you the status of the operations that are being performed in the routers itself. There may be some indication for failure, there may be some indication for internet, there may be some indication for incoming packets, there may be some LED status for the power. Yes, exactly, the power of this is the biggest example. You have so many LEDs on systems where you need to power on and power off the device. So whenever you power on the device, you will get to know that the LED is lit up. So these LEDs are nothing but the output device. Then there's another example, which are speakers. So for example, if you have mobile phones and you have your keypads on those mobile phones right now, so you must be dealing with the touch mobile phones. But let's take an example. If you have a keypad, or for example a touchpad, where you just touch your mobile phone, you press a key, you give it some input. Now whatever you're doing with your fingers, you are giving it an input. This is the manual effort, you are giving it an input. For example, on your phones right now, if you try to dial a number, maybe phone number, you will be providing your inputs. Now these inputs will produce an output. Now in this case, the output will be that the call will be dialed up with your mobile phones, and you'll be able to talk to other person on the other end of the that transmission link. So in this case, this is the output basically. So if we talk about sensors or any other input devices, it takes the input, embedded system takes the input and produces some output, so that you'd be able to use that output to produce some kind of result. So these are input and output devices for you. Like output devices, speaker is one of the example of output devices. You produce some music from the speaker, so that's an output device. And then moving on, we have sensors and actuators. Sensors we've already talked about, which senses some physical parameter and converts and digitize it, so that we can use the information and we can perform some operation on that data using the computers, using small computers or medium scale computers. In this case, we'll be able to use this data on our embedded system to produce some output. Now actuators you might have, if you are a robotics enthusiast, you might have really heard about motors in a robotic movement. So whenever you are working with LFRs in your college, if you might have observed, they have motors running clockwise and anti-clockwise, and in that particular robot you have your IR sensor in the front, which tells you when to do what. So basically that IR sensor is just another sensor which takes input, and using the value of that input, the motors are moved So we can say the motors are actuated. Actuators are nothing but the components which generate movements. In this situation, motor is an actuator. This is producing an actuator action. So the motor is moving because it is converting some energy that is going on, some input in your embedded system into your mechanical energy, because that movement is mechanical part. So the components which convert one form of energy to any other movement, it may be heat movement, light movement, or physical movement, mechanical movement, those are called actuators. Moving on, yes, system design. So whenever we talk about embedded systems, it's very important to know that, whenever you're starting on the design and development of an embedded system, it's very important to know the challenges of that particular embedded system. An embedded system is nothing but which is meant for one specific application. That is the one point that it makes it different from general purpose computers, because general purpose computer, like your laptops itself, in which you're able to do multitude of tasks. For example, you can play games, you can type, you can mail, you can do loads of different other things. These are general purpose computers. But an embedded system is just meant for one application, and it has to perform that one application really well. And that is why the size of an embedded system is very small in comparison to your general purpose systems. We'll get to the differences later on also, but this is the major difference basically, that an embedded system is supposed to work on one application specifically, and it has to do that application, it has to perform the task in that application really well. So some of the characteristics of an embedded system design is that your embedded system should be reliable. There should be a good reliability of your embedded system, because if you are not able to rely on your embedded system, if the end consumer is not able to rely on that embedded system, then I think it's not really worthwhile to put a system into the market and just waste your time and efforts and money in the process. So let's take an example of your refrigerator. Now your refrigerator, it has 2 or 3 specific jobs. Now these jobs, one of the major jobs is to maintain the cooling in your refrigeration system. Now let's say if you give it there's a dial in your refrigerators, and you want to tell the refrigerator that just maintain the temperature around 5 degrees Celsius, and I don't want you to go above 5 degrees Celsius. Now you are actually dependent on your refrigerator, because there is some food item in your refrigerator that demands that particular temperature. So if that particular food item, if somehow the temperature goes above 10 degrees Celsius, then your food will go rot. And if that is just an imaginary scenario, but still, if that is the condition, if that is your requirement of an embedded system, that you don't want your refrigerator to go above 5 degrees Celsius for one particular food item, and there's a dial, there's an input in the refrigeration that you just input your temperature and the refrigeration will take care of it. Now just consider this scenario. What if the refrigerator is not able to maintain the cooling around the temperature, and it gives you a false cooling at around 12 degrees Celsius instead of 5 degrees Celsius? Now this refrigeration will be unreliable for the end consumers. The end consumers will not be able to trust this embedded system. The end consumers will not really able to make full use of it. And so it's very important for an embedded system to be reliable in such scenarios, because in an application, in an embedded system, and where it has to perform 1 or 2 applications really well, your embedded system should be very much reliable to the end consumers, so that they may be completely or partially dependent on those systems to accomplish the task. Next thing is availability. Now your embedded systems, whenever they come into the market, it should be really available. The components of the embedded systems should be available widely in the market. Otherwise, what will happen is that, you know, the maintainability of that particular embedded system, the cost of that embedded system, the cost of repairing of that embedded system will be very high. So let's take a very simple example of a mobile phone whose component are really not available widely currently. Now that may be an imaginary situation, but consider a mobile phone. I'm sure you can very well relate to the situation where one mobile phone and the parts of this mobile phone are not really available in the market, and so the cost of repairing, the cost of maintenance is high. That if you somehow break the system, break that mobile phone, break any of that device, then the cost will be really high. And so the availability of these embedded systems, the components of these embedded systems that make up these systems, it should be really good. So it should be available widely in the market. Now the next thing is safety. Now whenever we talk about embedded system, we all know that, you know, these are very small embedded systems, and these systems are widely used in the consumer space, where they are used by the people who do not have the prior knowledge of these systems, because we are the developers, we have developed these systems and we know the ups and downs of these systems. So when these will falter, and when let's say not to touch these systems, and where not to touch these systems, and when not to open these systems. So these are some things that we need to take care of. In the market currently, there are so many safety standards that we'll not be getting into right now, but I think it's very important for you to know that for any system that comes into the market, that comes into the industrial space, that comes into a military space, that comes into a consumer space, they have their standards, they have their respective standards to conform to, so that the consumer will be able to use that particular device well within the limitations, and well within the boundaries of the device. So if that device somehow breaks that particular protocol, then I think it will be really not be useful for a consumer, and it won't be safe for a consumer to use that particular system. So in the market, what happens is, whenever there's a product coming out, usually these companies which make these systems, they have to conform to these safety standards, to, you know, so that their consumers will be able to use these systems without any safety issues, because the safety of a consumer space is also a responsibility of a product designer. So in that sense, safety is very important for an embedded system designer. Now the next thing is security. Now security, you must all have really heard about, you know, security breaches that already happens, and that has already happened in the past of the technological era. That be it any other any internet technology, be it any other computer system, you might have heard a lot of people saying that, you know, the system is hacked, the system was hacked. And giving you an example of a security breach that recently happened, there was a product of Philips, if you remember, Philips Hue lighting. These Philips Hue lighting bulbs, they were meant to they were basically RGB bulbs. So with the help of red, green and blue light, you'll be able to produce any other color pretty much. So these bulbs used a wireless communication protocol called Zigbee. Now it's not really important to know what Zigbee is, but what is important here is that they used a wireless communication protocol which was hacked later on. So there should be a very robust security in your embedded system. Otherwise, what would happen is that you design your product and you get it into the market, but some other company or maybe some other let's say person would be able to breach the security, breach the component of your embedded system, and maybe tweak some things into your system. Mainly when we talk about security, we talk about data, because data is one of the most important things in our space right now. And whenever we talk about an embedded system deals with data. It just takes some input, produces some data, and maybe acts on the data and produces some output. So it's very important for an embedded system designer to make sure that this data is very much secured. And mainly the security breaches happen when you want to connect your embedded system to internet, mainly in the internet of things space, where you want to send some data to the internet. Now maybe what would happen if your software is not robust, if your hardware is not robust, is that maybe some hacker using the same wireless communication would be able to breach the data, would be able to sniff the data. So it's very important to make your embedded system secure in that sense. Now coming on to the constraints part of an embedded system design. Now there are some constraints to the embedded system. We all know that an embedded system has a very small size, and it has a very small form factor, and it's very cheaper to the very much cheaper to the in comparison to the general purpose computer, the laptops that we are already working with. So some of these constraints are system memory. First of all, that you all know that in your laptops you have a good memory. You have right now maybe 4 GB RAM, 8 GB RAM, maybe 16 GB RAM. But these are general purpose computers. In embedded systems, you don't really need that much of a memory, because embedded system is dealing with one particular application. It's actually sufficient to to have a very small footprint, in this case. Let's talk about system memory. And if we talk about system memory, then an embedded system which has a system memory of 16 KB would be able to perform the operations that it is meant to perform. For example, maybe accumulate the data of a temperature sensor, and process it and send it to the internet using wireless communication, using a Wi-Fi, using Bluetooth, or any other wireless communication. Now in these embedded systems, we don't really need that much of a memory. We don't really need 1 GB or 500 MB of memory for that matter. All we can do is we can manage in just 16 KB or maybe 2 KB of memory in these embedded systems. So basically these embedded systems, they do not really that much of memory. So it's very important to know what are the constraints of an embedded system, and if you are designing an embedded system for one application, then what is the requirement of that application. So whenever you start developing an embedded system, whenever you start working on an embedded system, it's good to know the limits of the application that you are trying to develop or even you're trying to work with, so that in the later stage, whenever if you maybe come up with some challenge in that application, come across some challenge in that application, you'll be able to manage with that particular memory. So an embedded system has a lesser system memory, and most of the time it is sufficient. But if the application demands somewhat higher memory, then you would have to switch to other controllers as well. Then the other thing is available processor speed. Now available processor speed nowadays is a lot, basically 2 GHz, 4 GHz, and a lot, because right now though we have we've been dealing with Intel processors nowadays, and in the past we've been dealing with Pentium, and before that Core 2 duals, and now then I series of processor, i5, maybe i7 processor. Now in these general purpose computers, because you're doing a lot of things, you're doing gaming, you're doing you're mailing, you're using internet, you are developing some graphics on top in those systems, then these general purpose system, they need that much of a process speed, because they do not know what kind of application that you are dealing with, because a general purpose computer is meant for that. It's meant for multiple applications. On the other hand, in an embedded system, you don't really that much of a processor speed. a processor speed of maybe 12 megahertz, a mere 12 megahertz will do. For example, if I am developing a smart metering where I have to convey the electricity meter reading to the internet. Now, this is the application where I have to send the electricity reading to the internet so that you'll be able to see that data on the mobile phone, on the mobile application. So in that case, I do not need that much of a processor speed. I do not need a processor speed i3, i5 or Pentium for that matter, because it's not really my requirement. What is my requirement is that, under 15 or maybe 20 megahertz, I would be able to develop such a system which can send the reading, send the data to the internet without any fault. So embedded system, they have a lesser processor speed as well, and we don't really need much processor speed in embedded system, because partly because we are dealing with one particular application and the requirement of that one application is not that much. So this is another thing, that we need to take care of the process speed as well before going forward with the designing of an embedded system. The third thing is the power dissipation. Now, power dissipation is mainly it's directly proportional to the power consumption of your device. Now, in an embedded system, it's very important to know that if you are dealing with an embedded system which works on battery, then this power dissipation factor matters a lot, because a designer, embedded system designer, has to take care of the battery backup, the time that the embedded system would be able to survive with one particular set of battery. He should be able to know. Now, with that particular battery, with that, let's say 500 mAh battery, you have developed a system which just take the sensor readings and just send the readings to the internet. Now, it's very important for an embedded system designer to know what kind of power is being consumed in the embedded system, so that he or she would be able to know what kind of backup, what kind of battery backup that your device will be able to give you. Because the more power it consumes, the more your embedded system consumes power, the less time it will have on the battery backup. So it's very important to know how much power is being consumed on your system. So even if you're running an embedded system which is on alternate current, AC, basically power supply, let's say for example routers, we have Cisco routers, we have Cisco switches, they also have some constraints in mind, that after one particular point, after this power consumption, your embedded system should not be able to push that power consumption above that level. Otherwise it will not really conform to the standards. So that's where the power dissipation part comes in. So it's very important to know what kind of power is consumed by your embedded systems. Moving on, this is what you can see is the difference between the general purpose system and embedded system. As you can see that embedded system performs only a few applications that are known at the design time. So at the design time, what do you mean by the design time? Whenever you are starting designing or developing your embedded system, you should know what kind of application that you are working for, what kind of tasks that you need your embedded system to accomplish. On the other hand, in a general purpose system, you don't need such kind of requirements, because it has a good computing power. A general purpose system has a lot of applications. Basically, you may be using internet, you may be typing, you may be mailing stuff, you may be drawing in it, and lots of other stuff. So it's not really important to know the application in a general purpose system. An embedded system is not programmed by the end user. Now, what do you mean by the end user? The end user is a user which is using your embedded system. It's not someone who's developing or designing the embedded system. These are the users who are using your embedded system. In this case, they may be consumers. So for example, if you are designing a refrigerator, a washing machine, then your end users will be the consumer who are using these refrigerators and washing machines. So these people, they do not program the washing machines and refrigerators. It is the developers and the designers who program these embedded systems. In the case of general purpose system, these systems can be programmed by the end user. So you can maybe tell your laptop to do some other things. You can develop things on your laptop. You can tell your laptop to maybe develop a software inside which tells you the weather around the world. So according to the, that's the requirements vary basically. So in a general purpose system, you'll be able to program widely the end user. You are the end user. The end users are the one who are using the general purpose system. For example, the laptops that you're using, right now you are sitting in front of your laptops watching this video, the computer system that in front of which you're watching this video. Now this is something that you are doing, that you are watching this video, and afterwards you will be doing some other task. But this is something which is called a general purpose system, a system which has various application. In a embedded system, we have a fixed runtime requirement that if a washing machine is if you dial some timer on the washing machine, if the washing machine is not able to tend to that particular requirement and is not able to work up that particular requirement, that particular timer, then it will be a fault. It would be a fault of that embedded system. In the case of a general purpose system, it's not that case, because in general purpose system are basically used for wide applications. So the users and end users do not really care that the time which it takes, the time which a general purpose system takes to accomplish a task. So runtime is not really a big deal in case of general purpose system. Now the other thing is, whenever we are designing an embedded system, there's something that we have to keep in mind. One thing is cost. The cost of the embedded system should be really low, because these embedded systems are they have a very small form factor, and they will be widely used in the consumer space. So because these systems are used for one or two particular application, then their cost should also be reduced drastically, so that the end consumers would be able to adopt these systems into their ecosystem. Otherwise, what would happen is the end consumers would not be able to use this system in their daily life. So cost is a very important factor. You have to keep in mind before starting designing an embedded system, that what kind of cost you're looking forward to. The other thing is power consumption, that we had already talked about, that you should take care of your the part where you have to understand what is the power requirement of your embedded system. What kind of power requirement is there? What type of power will be consumed when it runs the software inside? So that's power consumption. And deterministic behavior. Now embedded system is widely known to run one application really well. It will just run one application or two tasks at best, and it will run those tasks really well. And those tasks should have a deterministic behavior. If at some point in time the end user notices that your device, your embedded system is behaving weirdly, then it will be a very bad thing for it will turn out to be a very bad experience for your consumers as well. So one of the most widely known example of an undeterministic behavior is when your embedded system, when your mobile phone gets hanged. That is the undeterministic behavior of an embedded system, because that is not determined by an embedded system designer. Because let's accept it, we all have faced these issues where our systems get hanged. Now we don't know when the systems will be hanged. There is one or the other requirement for a system to get hanged, but as an end user, as a consumer, we don't want it. It's undesirable for our system to get hanged. So a designer should know, an embedded system designer should know the deterministic behavior of these embedded systems. Now moving on is meeting time bound. So the embedded system should be able to meet deadlines. Now we will be talking about deadlines and time bounds in later videos of these webinars. But for now, what you should know is that your embedded system should conform to one time constraint. So if you say that your embedded system will compute your data in maybe 1 second or 500 milliseconds, then it should be able to do the same thing around that timing. Otherwise it will not be of any use. So the embedded system should has to it has to meet the time bounds. Now the other thing is size. Again, we've already talked about size, so the size should be small in the embedded system. In a general purpose system, the size is not that really a factor, because there's a very good processing power in a general purpose system, and that is why whenever you have a very good processing power, whenever you have a good capability, the size will increase. So that is why you must have seen that your systems, your general purpose systems like laptops and personal computers and iPads will have a bigger form factor than these embedded systems like smartwatches, like the Geofy device that you must have been using. So these are the example of some embedded systems and general purpose systems. Moving on, let's have a look at some of the examples. We've already talked about these examples. So one of these examples is a refrigerator. Now you can see that there are some features of refrigerator. One is that, maintaining the temperature, the actual temperature and required temperature. The actual temperature is the temperature which is maintained inside the body of a refrigerator, and the required temperature is the input that you tell your refrigerator to maintain. So for example, if you tell the refrigerator that I want you to maintain the cooling at 5 degrees Celsius, so that is the required temperature, but the actual temperature may be something different. So it may not be the case that you'll be getting 5 degrees Celsius, or you may be getting 6 degrees Celsius also, 7 degrees Celsius also. So an embedded system is not just it's not a system which gives you an exact output, but it should be able to give you a deterministic output. The embedded system designer should know that there should be a tolerance of 1 or 2 degrees Celsius. If you tell the refrigerator to cool at a 5 degrees Celsius temperature, then it should be able to do it under maybe 1 or 2 degrees Celsius of tolerance. So that should be a deterministic behavior. Now this refrigerator, as you see in the slide, it has an embedded computer. Now this embedded computer is nothing but a controller. A controller is just a computer with some peripherals. Now this computer, as you can see on your screen, will have peripherals just like alarm and displays connected to it, so that you can see the display of the refrigerator. Some of the refrigerators come up with a display which tells you the temperature which they are maintaining right now. And there are also some smart refrigerators which are connected to your Wi-Fi. So if you go out and if you are going out on a vacation and you want to know your refrigerator is working fine, then a smart refrigerator is a good way to go. It will tell you with this network interaction that the refrigerator is working fine and it is doing the cooling at the required temperature that you had set before going on a vacation. So there's a bit of human interaction also involved in an embedded system. So in an embedded system, you give an input and you produce an output, like we had discussed in our previous slides. So you would just give that system an input so that that system would be able to produce the output, and the output should be really productive. So in this case, in the case of refrigerator, you are inputting some temperature with the help of keypad. Now this keypad is taking your input, and the output is the temperature which is maintained inside the refrigerator body. That is the output. Now let's say if if it is if the topmost compartment of a refrigerator is frozen, and you have configured your refrigerator that if it is frozen, then just give me a notification. Then with the help of an alarm or some kind of notification from the network, from your Wi-Fi, you would be able to tell that now it is frozen, now it is time to just take it out. So this is one example of an embedded system. Moving on. Now most of the time in our consumer space, we fail to realize that just as much how many embedded systems are we surrounded with. Now if we talk about televisions, we talk about cars. These are not exactly the cars, but the system, the subsystems that are used inside the car. For example, the music systems that we have, the lock system, electronic lock system that we have, the sensors that are embedded inside a car. These are some of the examples of embedded system. A television, a controller and a system working inside a television. This is also a good example of a embedded system. So in as you can see on your screen, in this car you can see there's a lock system, you can see there's a sensor, and there are control buttons. Now these control buttons are nothing but your input. This is your human interaction, as we had discussed already. You give some input to this, and it produces some actuator activity. So in this case, you notice that whenever you push a button, whenever you give it some input, whenever you pull that particular handle, there is one particular mechanism around the car door which makes it open, which makes the car door open. So that is the actuator working. As we had discussed, the actuator is nothing but it actually generates some movement. It's a component that generates some movement. So these are just the actuators. Now if we also have sensors in our cars, nowadays, whenever we are reversing our car, there are sensors on the back of the car which tell you how as to whether there is an obstruction behind the car or not, so that you'll be able to get a good notification before you wrap up your car and get your car damaged. So this is one example of an embedded system. Now the question comes, why is there suddenly an interest in embedded systems, and why not anything else? Well, partly because that processors and controllers, they are they're getting reduced in size a lot, because as you have already noticed, you might have already noticed in technological trends that every year the area of the chipset of any computer, of any computing device, gets halved. If you have heard of Moore's law, I would not get into that, but you can search it on your own, Moore's law, which tells you the size and the other factors of a chipset that varies from year to year. So that embedded systems, the sudden interest that has come in the field of embedded system is partly because the technology is getting really cheaper nowadays. Now if you compare the technology from 10 years back, you have mobile phones at your disposal right now. 10 years back, who would have known that you would be using a smartphone to browse the internet? In the earlier let's say a decade ago, we did not have smartphones. We just had phones which we could we could be able to call the other guys and maybe text messages, but not so much of a smart. But what happens is, right now the technology is developing very rapidly, and with this rapid change in technological trends, the processors, the chipset of a processor, the size of these processors are reducing. They're being reduced rapidly. So that is one of the reasons that there's suddenly a surge in the use of embedded systems, and in industries as well. So the second thing is power consumption. Now earlier what used to happen is, whenever we used to see the mobile phones, let's see those mobile phones, if you might have noticed, the power consumption of those devices would not be that the power consumption would not be that good than what we are using right now, just because the kind of chipset that we're using. So power consumption is also one factor that has come into being. The more we are going ahead with the technology, the more better power consumption of devices that we are getting. So right now, we might be getting some devices which are consuming less power than the devices that are consuming that were consuming power earlier. So earlier we were getting some refrigerators which were maybe consuming more power than the refrigerators that we are getting right now. So power consumption is also one issue. So the power consumption has reduced very drastically in these embedded systems in the recent years. Now the other thing is cost. The cost of the processors and the other chipsets have come really down, and down to a level that the end consumers, the middle class of any economy would be able to afford. So these cost of processors have been reduced a lot. So that is why there's been a certain interest in embedded system. Really, you would want to go tomorrow and buy some device, let's say iPad, just because it has now become affordable. And maybe when we had iPods back then, we had this craze of buying those devices, and then when the later versions came into being, we were crazy about those devices as well, just because the cost was reducing. The cost of a transistor on a chipset, the cost of an IC, the cost of an integrated circuit on a processor, on a controller is reduced, and hence the cost of the whole system, the cost of the products nowadays are reduced. Now you'll be getting mobile phones at a very cheaper rate. The smartphones that we talk about nowadays, you might be running in Android and iOS smartphones. iOS being Apple iPhones, and Android being so many other phones like Samsung and the other mobile phones. 5 years back, who would have imagined that you would be able to afford a smartphone in at such a cheap rate? So that's what it is, that the cost of processor have come down a lot, and that's why the cost of these embedded systems have also come down as a result. So this is one aspect why there is a good interest in embedded system nowadays. And now there's a greater awareness in the electronic system around you has also resulted in consumer using those electronic system. You might have noticed that earlier the consumers did not have much knowledge about the electronic devices around them. So nowadays the technology trend is such that even a small kid would be really aware of the electronic system, of the mobile phones, maybe of the iPads they're using, of the processors that you're using, even though they might not know the basics of that processors. But that is the irony of it. A small kid would be knowing what kind of electronic equipment he's handling. So that is one good thing about this technology, that there's been a very good awareness about the electronic components in the recent years, and that is why this boom in embedded systems. Now the other thing is that what happened, let's say the use of these embedded systems have been really increased in recent years, but what would have happened if we did not have the means to develop on these embedded systems? Now the last thing that I want to concentrate here is that without the development setup of these embedded systems, we would not have been able to achieve the kind of accuracy, the kind of penetrability in the market that we have, the embedded systems have right now, because they have these development environment already set up, the emulation environment where they can really see on a computer machine that how their embedded system would be able to behave. So one example of this is that you might have worked with virtual machines where you basically emulate the behavior of an operating system. Similarly, we also have emulators for these embedded systems where you would be able to know the behavior of an embedded system, how an embedded system would behave in which scenarios. So that is one great thing of these embedded systems, that in the recent years, in the recent times, there have been really increase in the development, in the testing platforms, in the development platforms and debugging platforms, so much that the design cycle is reduced a lot. So for example, if you were able to design an embedded system last year, if that time was maybe 3 months, that 3 month time would be possibly reduced now because of the improvement in the trends, because of the improvement in the testing cycle, because of the improvement in the development cycle that you have right now. So this is also a good thing, that the development environment keeps on improving. The simulation and emulation of those embedded devices also helps a lot to they help these embedded systems to penetrate the consumer market, so that the development time is reduced a lot. So if I'm developing embedded systems, I would be able to debug it and maybe modify the software if need be, at a very reduced cost, and I would be able to do it in a reduced time. So that's what a good thing about embedded systems. So these are the reasons why embedded systems have been really talked about topic, and partly also because that there has been a very good boom in Internet of Things ecosystem that we'll be talking about in the later videos, but for now this. And then let's talk about microcontrollers for a while. Now whenever we talk about embedded systems, we have to talk about microcontrollers. It is imperative that we talk about microcontrollers when we are talking about embedded systems, because embedded systems are nothing but systems that have the capability to compute something. They have the capability to act on some input and produce the output. And but we have to ask questions: how come an embedded system is able to do that? It's with the help of this particular device, this particular component that you see right now in front of your screens, microcontrollers. So microcontrollers are nothing but it can be described as a small computer which has the capability of computing, which has a processor and attached peripherals to it. Now whenever we talk about peripherals, we talk about inputs and outputs. So I would like to start the discussion on peripherals with the example of keyboard and mouse, because in a general purpose system as well, we have a keyboard, we have a mouse with which we provide inputs, and maybe there are some peripherals which give us output, for example speaker. So these are called the peripherals of a system. So in a microcontroller as well, there are some peripherals. For example, there are some general purpose input output pins with the help of which you would be able to take some data from the input pins and produce some output on the output pins. So on the output pin, maybe you have put some LED which may blink, which may regulate the brightness, and on the input side you might have interface a sensor which is taking the reading. So these are general purpose input pins, which is a very important part of any microcontroller. Now in a microcontroller, as you can see on your screen, you would have a processor to process the data, as we had already discussed, and we'll be discussing about processor in the next slide as well, which it just processes the data, the intermediate data, and gives back the result. As you can see, ROM RAM, as we had already discussed, that read-only memory, which is this is the kind of memory, non-volatile memory, which retains the content of which basically retain its content even after you switch it off and switch it back on. So you'll be able to retain the content of this memory. The example I would like to here concentrate on the kind of software that we deal with. Now we all know that embedded software works in the combination of hardware and software. So what is this software? Where is this software stored? Now this is the component where your software is stored. This is where your software will be stored even if you switch the controller, even if you switch the embedded system off, and if you switch it back on, the content will be retained in this memory. So, and there's another memory, RAM, like we had already discussed, which is not able to retain the content of its memory, and if you switch it off, you would not be able to get back that data afterwards. So basically RAM is used for processing the temporary data and produce some output, so that the embedded system may be able to produce some output actions, some actuating actions. So this is mainly used for some intermediate operations, some processing. All the processing is done in this memory, random access memory. Now we have timers, serial communication, and input output ports. We'll be discussing these things in the later videos because they are more advanced, and I don't think that I should overwhelm you with the details in this video. So these are some other components that we'll be discussing in later videos, but basically these are the parts. Also, I'd like to concentrate on this clock circuit part here, that a clock in a microcontroller is the heart of a system. Like in human beings, we have heart which keeps on beating and pumps up blood continuously so that our life goes on. Similarly, the clock circuit is used as a heartbeat to this microcontroller, so then the microcontroller keeps on running and doing its task. So these are some of the components of a microcontroller, which is basically nothing but a computing device which has memory and some peripherals embedded into one. So it's just basically an IC, an integrated circuit, which has all these components into one. Let's move forward with microprocessors. Now, in comparison with microprocessors do not have the peripherals. Like, for example, I'll just move back to the slide here. You can see the digital to analog converter, the input output ports, ROM, RAM, timer, serial communication, and ADC. Now these are the peripherals of a microcontroller, of any system. These are the peripherals. These are called the peripherals of a system. Now in a microprocessor, we do not have the luxury of having these peripherals. A microprocessor has just one job to do, and that one job is to process. Now, what do you mean by processing? Like we've already discussed in the earlier slides, that you process some intermediate data, you perform some arithmetic logical operation, and you produce some output. How do you produce these outputs? How do you perform these operations? Now this is your answer. Now in a microprocessor, you have some parts like ALU. ALU is the most basic part of any microprocessor. Like even if you are working with a very powerful microprocessor, even if you're working with a laptop which has an interprocessor, it also has an ALU. The definition of ALU is, it's basically an arithmetic logical unit, which the name itself suggests that takes care of arithmetic and logical operations. Maybe you would want to do some addition operation on some data, maybe some division operation on some data, and produce some output. So this is where this comes in, and then this is the bus, analog bus. We'll come to that in the later videos. It's not really that important right now. And then comes on the part with registers. Now registers are the temporary storage. They are the local storage which stores the temporary data of these operations. So for example, if you tell your processor that if you want to perform the addition operation, and in order for the microprocessor to do it, those two quantities, 2 plus 2, and you want to produce output 4, these quantity will be stored in these registers, and then it will be processed using ALU, and the result will be put back to these registers. So this is where ALU and registers are used. Now we have IO ports that we had already discussed, but the main difference between microcontroller and a microprocessor is that a microprocessor does not have this luxury of having peripherals like a microcontroller. Like you have already seen, you have timers, like serial communication to communicate with the outside devices, and memory to store the software into it. So you do not have such luxuries in a microprocessor. Moving on, Now, I think it's good to know the difference between a microprocessor and a microcontroller. Now, a microprocessor is just a standalone device. Microprocessor is can be considered as a heart of a system. Can be considered as a heart of a microcontroller. Now, microcontroller, on the other hand, will have the memory, the RAM, ROM, input, and timer. They are all embedded in the single chip. Microcontroller is just one IC where you get where you have the luxury of having CPU, RAM, ROM, and IOs, timers, and all the other peripherals in a single chip. On the other hand, in the microprocessor, we do not have such luxuries. So what happens is, whenever you are designing a microprocessor, then you would have to deal with such requirements that you would have to interface the peripherals like RAM, ROM, IO, and timer separately. So you, with the microprocessor, you just get a CPU, the ALU part, like we had already discussed, the ALU part, the register part. This is the microprocessor. But in a microcontroller, it is all embedded into one. In a microprocessor, you have to interface. The designer has to interface these peripherals, RAM, ROM, IO, and timer separately, and so the cost is on a higher end. So the designer can decide the amount of RAM, ROM, and IO ports, because because the designer is actually interfacing these components afterwards. So he or she can decide what kind of RAM, ROM, or what are the number of IO ports that he needs to interface into the processor. On the other hand, in the case of microcontroller, it's very much fixed. It is very much fixed. So the RAM, ROM, and IO, you won't be able to change that. The designer will not be able to change that because it's on the single chip. On the other hand, in a microprocessor, the microprocessor will be one chip, and these peripherals will be interfaced separately. That is why the designer will be able to decide these RAM, ROM, and IO ports. Now, going forward with the microprocessor, we have high processing power, as you all know. In microprocessor, one of the basic example of microprocessor is the processor that you are already using in your laptop, Intel processors, which has a very good processing power. Now, in your laptops, what's happening is that your hard disk, your RAM, it is interfaced separately. As we had already discussed, in a microprocessor, it has a separate connection of RAM, ROM, and the other peripherals. In your laptops as well, you have an Intel processor, and interfaced with this processor, you have your RAM, you have your hard disk attached to it. So you would get a high processing power because you have the luxury of choosing what kind of processing power, what kind of processor that you want in your laptop. So that's why the term comes in that you configure your laptop. Whenever you go to the market and you want to buy a laptop or a computer, then you can tell the salesperson that you want this configuration, you want the processing power to be like this, you want the hard disk to be like this. This is the reason that these parts are assembled separately. I'm sorry, these are assembled, but these are made separately. The processor is made separately, and the peripherals like hard disk, the RAM, and the other things, for example, the audio card, these are made and prepared differently, and so they are assembled. So you would have the luxury to choose between them. On the other hand, in a microcontroller, everything is pretty much the same. So on one piece, on one IC, you would get the same thing. So you don't have the luxury to decide the kind of RAM, ROM you have. You would have to do it in just one go whenever you are buying one microcontroller. Otherwise, at the later stage, you would not be able to do it. So also microcontroller, they have low processing power in comparison to microprocessor, and because microcontrollers are usually used in embedded systems where the form factor is low, where there is only one or two applications that need to be taken care of. So the power consumption is also low, and processing power requirement is also low, as we had already discussed that we don't need that many applications to run, as in the case of general purpose computer, which uses microprocessor, and they have this high power consumption because they might be running different applications. You might be running Microsoft Word right now, and maybe there's a game running behind on the background. and you're watching this video, so there are background tasks also which are going on, multiple applications in a general purpose system. So that's why the higher power consumption in the case of microprocessor. So in the microprocessor, they are typically 32 and 64 bit processor, and in microcontroller they're specifically 816 bit, but that's not really true, and we'll come to the part later on, that what is this 64 bit and 8 bit 16 bit. This is basically the architecture that they follow, the addressable memory that they deal with. So no need to tire yourself up with these facts right now. We'll be getting into all these things in the later videos. So then comes the general purpose, as we are already discussed, that microprocessor. In the general purpose computer, we have already been using the interprocessors and the other processors which has a very good processing power, and in this case microcontrollers are used in embedded systems, a single purpose means single application for single task, maybe, so that you'll be able to perform that one task really well with the help of low processing power and consuming less power. Microprocessors are considered to be less reliable because of the fact that they are actually dealing with a lot of applications, and you don't need your general purpose system to deal with one or two just application. That is why it's less reliable, and it is just okay to use it in applications where we just have to deal with multiple things and not necessarily deterministic. In the case of microcontroller, it's highly reliable because of the fact that they deal with one or two applications, and they just focus on those two applications, those tasks really well, as in the case of embedded systems we've already seen. So for example, the Geo-Fi device that I am using right now to connect my laptop to the internet, it is just performing one task very well, one or two tasks really well. It is connecting my laptop to the server, and also it is giving me the indications, LED indications. So the embedded system, they concentrate on less things, but they do it quite reliably. That's why they consider really reliable. Now the example of microprocessors are 8086, 8085. Like you must have already studied in your academics, in your college courses. Considering you have not studied about these processors, we'll be discussing about all these things in the later videos. This is just an introductory webinar session so that you would get to know one-on-one with the embedded system and the kind of design that we already have in the market. One of the example of microcontrollers, 8051. So yeah, how to get your hands dirty, how to get started with the embedded system development. There are two things basically that comprise of an embedded system: hardware and software, as we have already talked about. Now, in order to do the hardware development, we should know what is a hardware development. In what sense we are talking about hardware development when we talk about embedded systems. So hardware development is nothing but choosing the right hardware for your needs. Now as we already know that you put the software into the hardware and to produce some output, providing some input. Now as an embedded system designer, you should be able to know what kind of application that you are dealing with, what kind of constraints that your hardware has, what kind of environment that you will put your hardware into. Maybe this hardware will be put to some place where it's very cold. Maybe your hardware will be in a place which is very hot. Maybe your hardware will have 5 peripherals. Maybe it will have 10 LEDs and stuff like this. So basically you should know the requirement of your application. You should know the requirement of your current project, what you are handling. Only then you will be able to choose a microcontroller. As we had already discussed, microcontroller takes care of the computing part, and it's just basically a small computer in an embedded system. So then only you'll be able to know how to choose a microcontroller, because microcontroller comes in variety. How would you choose a microcontroller? One microcontroller may have 10 input outputs, the other microcontroller would have 2 input output, but will be cheaper than the former. So in that sense, you have to choose the microcontroller. So you've got to know how many IO ports you want, how many input and output pins you need, how many input and output channels you want. For example, in an embedded device, you should know maybe how many LEDs you want to light up and how many buttons as an input you want to take. So these are all the things that you should know. Also the memory requirements. Peripherals will come to this part later on, but memory requirements, you should know what kind of memory that you're dealing with, what kind of memory, the storage, and the RAM will be sufficient for your needs. Maybe there comes a time where your embedded system might not be able to satisfy the need of the improved situation. So for example, what happened is, when I was working in my last company, we had this product where we used to deal with sound-based transaction, and for the last 1 year we had been working on that one particular system. But now let's suppose that we had a 16 KB of ROM. Now we had developed quite a lot of things in that system, and not getting into the specifics of that product, but we had a lot of things, a lot of features in that system that we had developed over the course of time. But there came a moment when from our superiors we had this requirement that we are supposed to add one functionality to it, add 2 or 3 functionality to it. Then we encountered one situation where the memory was not sufficient for our needs. So that's what happens when you don't really design your embedded system well. You have to take care of the requirement, but you've got to know what are the memory requirements of your system. Maybe 1 year afterwards you would need a greater memory than this. So take care of all these parts whenever you are designing in embedded systems. So similarly, you've got to know the processing speed, what kind of speed you need, and the power requirements, what kind of power requirements that you want for that particular embedded systems. So that's pretty much about the hardware development that you need to know right now, because we'd be going deeply into these topics afterwards. But this is pretty much it for the hardware development part, and then we'll move on to the software development part. Now, for those of you who are very interested in developing software and who wants to really get into the field of embedded systems, I would suggest you to learn the basics of C, because in my career I have seen that most of the embedded systems, they work on C or C++, but for now C is being used widely in the embedded systems. C++ are used, the language which is used widely, basically because the modularity of C++ is really good, the maintainability is really good in C++. But if you want to start software development in this particular field, the embedded systems, then you should definitely know C, and you should right now concentrate on improving your grasp on this programming language. We will also concentrate the programming part in the later videos, and we'll come to the programming aspects of it. But right now what you should know is that in order to develop a software on your embedded system, in order to develop a software for your embedded system on any other requirement, there are 3 things that you need to do on pretty much on any platform that you have, be it any microcontroller in the market. The first thing is you have to come up with some algorithm. So for example, you have an application which just senses the data around the environment, the humidity of the environment, and tells you the data. Now you've got to know the algorithm with which how you are calculating the humidity, because humidity sensor is giving you some data. You have to convert that data into some particular value. Now the algorithm basically deals with the mechanism part of it, how you build up your software, how basically what are the things that your software need to follow in order to come to a conclusion. So maybe if you want to search stack, search in a stack, then there are some rules that you need to follow. Now this is just a vague example, but what I need to focus here on is that for a software development to get started on an embedded system, you should know what kind of algorithm that you're using, and also the language that you're using. Now there are two options that we have when we talk about embedded systems, and two widely known languages are assembly, which is comparatively a lower level language, than C, which is a high level language. Now what is the difference between the two? Now you might have already you might know the difference or might not know the difference, but let me tell you that assembly, you deal with assembly when you know a good deal about the instructions of the processor, when you know a great deal of the instructions and the other pipelining that is being done in the processor. So you need a greater level of knowledge of processor if you want to develop an assembly language. On the other hand, a high level language takes care of all the other things, and you just need to take care of the algorithm part, and you still need to know the specifics of processor, but you don't need to know the exact instructions that you need to follow. Now there are some move instructions, some branching instructions, some addition instructions that may vary from processor to processor. So if you are working on one processor and you develop some assembly language using some algorithm for an application, then the other processor might not use the same assembly. So it's very important to know that if you use C language, then it will be very much portable on the other family of the same processors. On the other hand, the assembly language, you might have to deal with some modifications, actually a lot of modifications most of the times. Lately I had been working in some digital signal processing application where we had to optimize our algorithm for one particular processor. But what happened was that whenever we used to switch to some other processor, the assembly instructions used to differ, because it's not hard and fast rule that one family of processor will use the same assembly instructions. So it's very important to know what are the requirements of your embedded system. If you are just developing it for one particular family, then it's good to know, or if you have a good understanding of assembly language and assembly instructions, then it's good to develop things on assembly. But I would recommend that you start developing on high level language, and this is a good way to go for the beginners right now, because assembly language needs a very thorough understanding of your processors. So for the beginners, this is the way to go. High level language, C, you can use C, you can use C++ as well, and we'll come to those parts later on. But for now, I would advise the audience to be thorough with the C basics, so that it would help in the later videos when we start developing and start getting our hands dirty on the programs, on the real life examples. Now the other thing is using a compiler, assembler, and a linker. Now if you have used a software, a C, for those of you who already have the knowledge of C, then you know that there are some steps that are that happen in there are some steps that are followed in order for the high level language to get converted into a machine language. Now a high level language is just a language that that is understandable by humans, us, because the high level language was introduced for human beings, so that the people like you and me would be able to generate algorithms and produce some really good output based on that. So high level languages were meant to for those applications. But the computers nowadays, or in the earlier days as well, they need machine instructions. These computers, they deal with zeros and ones. They do not know the difference between the syntax and the semantics. They do not understand it. They just do not know high level language. All they understand is the language of 0 and 1. So if you give them 0 and 1, only then they would be able to produce some output. And it goes the same for any other electronic system, whether it's a general purpose system or an embedded system. The concept is the same, that these systems, they understand the language of zeros and ones. They do not understand the high level language. So it's very important that you give them 0 and 1. So compilers and assemblers and linkers, they are ways to convert this high level language into the machine language, into the language that is understandable by the machine. We'll get to the compiler part also in the later videos, so no need to worry. Now the last thing that we need to concentrate here is the debugging. You need to debug your code, and it's very important that whenever there's problem in your embedded system, that you should be able to debug at least where the problem comes and where you should be able to solve it. C versus assembly. Now there's quite a bit of debate in this, that when should we use assembly language. Assembly programs, however, they are more optimized than C programs, but they're really hard to develop. And that is why I advise the beginners and who are starting with this embedded system software development, I advise them to start with C, because it's very complicated and you need a thorough knowledge of processor as well for the instructions because assembly language is all about instructions, putting instructions into it. So you need to have a good grasp for processor as well. So that's where the C programming language is good, where there's a flexibility and fast development. Now comes the part of applications. Where are these embedded systems used? Now, up until though, you might have really understood the importance of embedded system and where they're being used. Some of them are being used in the wireless routers that you are using right now, the internet connections that you are using right now. These are embedded systems. The gaming consoles, the ovens, the refrigerators, the MP3 players, the digital cameras, they are all the example of embedded systems. We are all surrounded by so many embedded systems that we might not even realize. So I give you this task to observe your surroundings and count the number of embedded systems that you have right now around your workspace, and let me know in the comment section how many embedded systems are you able to identify. And now a lot of people talk about scope and career possibility of embedded systems. Now, as you might have already understood by now, that the embedded systems are present everywhere, from the consumer space to the industrial space and the military space. In the militaries, they're used in weaponries and communication system, the satellite systems, even the Mars rover that is being run there on Mars. They have a very basic embedded system going on there. And these mobile phones that we use, the laptops we use, all these things, the cars that we travel in, they have subsystems, they have audio systems, they have sensor systems. All these are example of embedded systems. And though there's a vast possibility of embedded system in the space, I would take up all the doubts and anything that is related to the earlier slides as well, and you can ask me your doubts specific to those things. That for example, if you want to know what kind of career opportunities that we already have in the market right now, I'd be able to tell you, and it's a lot, by the way. So I would be taking the questions for those and not be covering in these slides. But just to sum up, there's a huge scope in embedded systems, and if you want to develop software, if you want to develop hardware, there's a huge scope in the market. Whether there's a consumer space where the consumers and as people, we are using the televisions that we're using, the mobile phones that we're using, the iPads that we're using, the Kindle devices that we're using, or the industrial application, or maybe the military applications where there are some communication equipments that are being developed nowadays, some radars, some sonars. These are also some of the examples of embedded system which are used widely. So there's a huge scope for embedded systems and huge number of career opportunities which we'll be getting into, and these are some of the resources that I would like you to go through. And um, this one particular book. Oh, one second. I'm really sorry. Well, this one particular book that I was pointing to, which is here, this Embedded C AVR Microcontroller Embedded System by Muhammad Ali Mazid. It's very good. So I would recommend you to go through it at length, and it will have all the basic knowledge of embedded system that you have right now, and a very small amount of information that is shared in these slides. So you can always refer to these slides. And the other references are also, nowadays you also have so many courses on edX and Coursera on these embedded systems, and I would recommend you to go through the free courses for now, not the paid courses, because there's a huge source of information on the internet from where you can get a good understanding of embedded systems. So I would like you to go to the free courses first before going for the paid courses. So these are some of the resources, and thank you so much for your patience. And any doubts that you want to clear up, you can let me know. I would be coming live, or you can throw the questions in the comment section. I would be taking those questions, answering all your queries relating to the embedded systems and the earlier slides that we had, or anything that you would like to ask, basically. All right, thank you, be well, and thanks for your patience. See you later in the later videos of the webinars.